So we start off with our first unit, rationalizing radicals and two-term radicals, right? So starting off in this unit and in this lesson, first was to simplify and remember what is a radical. A radical is described to use a root, right? So it's anything under the square root or anything just under the root symbol, right? And then why do we rationalize? We rationalize because a root, example, 3 to the power or 3 over 2 square rooted, you cannot be leave in the denominator, right? We can't just leave root 2 in the denominator. Root 2's always have to be back in the numerator. They always have to be back in the top. You can never have a root 2 in the denominator. And I'll show you guys why in the next slides. Okay, so now to dive into power rules. So what power rules do is that it helps us find the derivative of functions that involve exponents. So the main formula we use here is d over dx, x at n is equal to nx to the exponent of n minus 1. So I know this looks a little bit confusing, but it's really not too hard. So the d over dx just means we're finding the derivative with respect to x. And when we have a function like x raised to the power of n, so x to the n, the power rule tells us to do two things. So bring the exponent down and multiply by the x. So the n comes to the front. And then subtract 1 from the original exponent so that the new exponent becomes n minus 1. So now we'll look at some examples just to make this more clear. So imagine we have the function, yeah, we have the function x to the power of 5 using our power rule formula. So d over dx to the power of 5 would give us 5x to the power of 5 minus 1, right? So then that would just become, when we bring the 5 down and subtract the 1, it would just give us 5x over 4. All right, that one's pretty simple, that one's pretty easy. Now, what if our exponent is a decimal? So now when we have x to the power of 2.5, the rules still work. When we have d over dx, with x to the power of 2.5, it would just be equal 2.5x to the power of 2.5 minus 1, which would become 2.5x to the power of 1.5, right? So it's generally so easy. You would bring it, make it simpler, you would multiply the coefficient with the exponent, and then you would subtract one um from the numerator. So, or sorry, you wouldn't multiply the exponents. You would make it that exponent. So if we have x5, we would just make it 5x. And then we would always just subtract that by 1. It becomes very simple. So now again, when we have x to the power of negative 3, we would bring the negative 3 to the front, make it our coefficient, and then we would subtract it by 1. Now remember, it's negative. So negative 3 minus 1. Lots of people think, oh yeah, it turns into negative 2. It actually turns into negative 4. I know subtracting negatives everybody knows, but people get it mixed up in the exponents because there's already so much to think about. So yeah, people can get it mixed up in the exponents here. So then it would become negative 3x to the power of negative 4. And then lastly, when we have x to the power of 5 over 2, this is with a fraction now, it's nothing different. You would bring the fraction to the front, it would become our coefficient. So then 5 over 2x, and then you just subtract it by 1, so 5 over 2 minus 1 minus 1 would become 3 over 2. So then 5 over 2x to the power of 3 over 2. So it's very, very simple. You get it within it's 2 steps. It's a 2-step process, and it's very easy to do. All you do is bring exponents to the front and then reduce the exponent by 1. There should be no issues solving it here. So now we're going to connect this with algebra. So our first examples show us how we multiply numbers and variables, or numbers and special math symbols called radicals, which I've explained earlier. So when we look at this, if we have 3 times a, we write this as 3a, right? That's pretty simple. We learned that before. And it's like saying it works the same way with radicals, because if we have 3 times the square root 2, then we would write it as 3 square root 2. It's almost the exact same thing, right? So the number just sticks to the variable or the radical. It's like pretty simple. And then we always have to combine like terms. That's a big rule here. We can only combine like terms. So when we put things together in algebra, we can only collect like terms. So um, for example, when we have 3a plus a, um, then it's like saying, for example, if we have three apples and then we get one more apple, how many more apples do you have, right? It's four apples. But in algebra, 3a plus a is 4a. And so the example says 3a plus 3a is 6a. And that's another great example because we have two groups of 3a. So we add the numbers in front called coefficients. So 3 plus 3 equals 6. And that makes 3a plus 3a equal 6a, right? And then it works the same exact way for radicals. So if we have 3 radical 2 plus 2 radical 2, notice that both terms have radical 2 in them, right? It's just like the variable, like what we did for the variable. So since they're like terms, also just to mention here, under it just because it's a radical doesn't mean they're like terms. They have to be the same number radical too. So now that's like terms, we just add the numbers in front. 3 plus 2 equals 5. We get 5 radical 2, right? And then I'll show you here. So like when we do unlike terms, like the different numbers. So this is what I was talking about earlier. So when they aren't like terms, we would see like 2a plus 2b. We have a and we have b. They're different. So we can't combine them into a single term. We just leave it as 2a, 2b. It's like I said before with the apples example, if we have two apples and two bananas, you can't just say you have four apples and like apple bananas, like it doesn't make sense, right? So same thing would apply to radicals. If we have two radical 3 plus 2 radical 2, the parts under the square root, like the numbers, they're different, right? So it's not like terms, we can't combine them. It would just stay as 2 radical 3 plus 2 radical 2. Okay, so now we'll show why basic technique does not always work, right? So in our example here, let's say, so we have 3 over radical 3 minus 1, right? And sorry, I don't know why my camera's going out. Okay. And our goal here is to just get rid of the square root in the denominator. So we want a rational number there. Now, a natural first thought might be just multiply the numerator, the denominator by the radical part of the denominator, which is radical 3. So let's try that, right? So we do 3 times radical 3 over radical 3 minus 1. It's like what we did in the previous example times radical 3, right? So then we would get 3 radical 3 over the radical 3 minus 1, radical 3, which becomes 3 minus radical 3. And then if we distribute the radical 3 in the denominator, we get 3 radical 3 um, over 3 radical 3 over 3 radical 3. And then this will just give us our general answer. Okay, so now where's the problem here? We still have a square root in the denominator, don't forget, right? So multiplying by just the radical part of the denominator only worked when it was a single term, right? But now when we have a denominator that's two terms, like radical 3 minus 1, multiplying by the radical just moves the problem around because then, remember, it gets multiplied with the -1 as well. So it rationalizes one term, but introduces a new irrational term. So what's the solution? We need to use a special tool called the conjugate. And the conjugate of an expression like a minus b um, is a plus b. So for a denominator, radical 3 minus 1, the conjugate is radical 3 plus 1. And the reason the conjugate works so well is because of a handy of algebraic identities, right? Difference of squares. So when we multiply our denominator by its conjugate, we get the difference of squares. And squaring a square root gets rid of the radical. So yeah, that's generally how it works. You can't always use basic technique. So going back to what I was saying about conjugates. So we'll start from the beginning. What exactly is a conjugate? It's all about changing the sign between the terms in a binomial expression, like I was saying with the difference of squares. So binomial expression, it will be like a plus b or a minus b. And the conjugate is basically like its opposite sign. Like it's always the opposite sign of it. So when we look at an example, 3 plus radical 2, which I'm always seeming to use, to find its conjugate, we look at the sign between the 3 and the square root 2. It's a plus sign, so we flip it to a minus sign, and then the conjugate is 3 minus radical 2. It's just always the opposite, right? But now, if we have an expression that looks like radical 5 plus 3, what we would do, the term, so with the terms of square root 5 and 3, we have the sign between them that is plus. So we change it to negative. So the conjugate is 5 uh minus like negative 5 negative root 5 plus 3, right? So if one of the terms is radical, like square root 2 or square root 5, you change the sign of that radical term. In 3 plus square root 2, the radical is divided by or it's not divided by square root 2, it is square root 2. So we change its sign to negative square root 2. And in square root 5 plus 3, the radical is square root 5. And we change its sign to negative square root 5. So the other term always stays the same. And then if we look in another example here, the root 5 plus root 3. So here we have two terms, both radicals, and the rule says that we can change either sign of the radical term. So we have options for the conjugate, change the sign to negative root 5 plus 3, or just make it general root 5 minus 3. So both of these do count as valid conjugates, and we can choose whatever is easier, whatever makes more sense. I think radical 5 minus radical 3 makes sense. So generally just wrapping it up, when we find the conjugate, it's all about flipping the signs between two terms in a binomial, which is pretty easy. So now when we want to get rid of the denominator here, we would rationalize it. Okay, so when we want to get rid of the root in the denominator, we would rationalize it. So we would do what we did in the previous slide, which is using the conjugate. So we would multiply the denominator by its conjugate, which is negative root 3 minus 1, right? So now when we multiply the denominator by its conjugate, it's exactly like a difference of squares, what I said in the conjugate slide recently. So then it will just be like a minus b is plus b. So then it's like a squared minus b squared. And then in our case, a equals root 3. So a equals root 3. And our b is just b equals 1. So when we do that, we get radical 3 squared minus 1 squared. And then what's radical 3 squared? That's just 3. And then 1 squared is 1, so 3 minus 1 is 2. So now the square root is gone from our denominator, and we only have a single term. So now to keep our fraction equal, whatever we did to the denominator, we're going to do the numerator, so we're going to multiply our original fraction by negative root 3 minus 1 or root 3 plus 1, same thing, and this like multiplying it by 1, so it doesn't change the value of the function, of the fraction, sorry. And when we multiply negative root 3 minus 1 over negative root 3 minus 1, um our problem like now becomes that the denominator is already 2. So now let's look at the numerator. 3 times root 3 plus 1, or negative root 3 minus 1. And we would just distribute the 3. So 3, then it would become 3 times root 3 plus 3, which equal, or plus 3 times 1 actually, which would become root 3 plus 3. So then putting it all together, our new fraction is um, 3 root 3 plus 3 over 2. Right? And that's it. The denominator is now a nice rational number of 2, and we successfully rationalize the expression. This is often the preferred way because it's usually a bit more straightforward. And to rationalize a denominator with two terms involving a square root, we would multiply the numerator and the denominator by its conjugate, and then we would just use the difference of squares to eliminate the square root. So now to wrap this all up, we're just gonna talk about the golden rules. That's what I'm gonna call. I'm gonna call it the golden rules. right? So rule number one, we're just going to start straightforward. Whatever you do to the top bottom, you must do to the top. This is the golden rule of fractions that we've learned from a long time ago. If you need to multiply the denominator by something to get rid of the radical, you must also do it to the numerator by the exact same thing. So think of it like keeping a scale balanced, you know? If you multiply the bottom by, say, radical 5, and if you got to multiply, then the top would also be multiplied by radical 5. And this keeps the value of the fraction same and not uneven. And then rule two, when we use conjugates, we always flip the sign. This is the whole purpose of conjugates, that we flip the sign. So sometimes we have expression with two terms of the denominator, like a plus root b, okay? And then to get rid of the radical, we use something called the conjugate. And the conjugate is just the same expression, but with the sign with the terms flipped. So then the conjugate would become a plus root b is a minus root b, right? And then remember when you're finding the conjugate, you always change the sign. And then in the third rule, in a two-term denominator, things do cancel out, right? So this is where this builds up on rule two. And when you multiply a two-term denominator by its conjugate, something magical happens. Because of a special math pattern of difference of squares, the radical, in its terms in the denominator will always disappear. So leaving you with just a plain old rational number. And it's like the radicals cancel each other out. So like for example, I'll just make it up with variables. So x plus y bracket and then x minus y. So when you're multiplying those, it's x squared minus y squared, right? So the radicals just cancel each other out. And then rule four, obviously, don't forget to simplify at the end. After you've done all the multiplying and canceling, you'll have a new fraction. And your final step is to make sure it's as simple as possible. This means reducing any fractions, like 4 over 2 turns into 2, right? Like any basic simplification at the end of all the work. And then, so yeah, generally, just to sum it all up again, multiply the numerator and denominator by the same value, change the sign of the conjugates, and then remember that terms cancel out, especially with conjugates and with rationalizing, and then simplify in the end. So keeping these rules in mind and rationalizing denominators will become so easy. So that should be it.